Alright, so I'm going to go to the rest of data summarization and move on to classes and bleeding. This is going to be a brief foray into visualization a little bit, but we're going to have a fuller lecture on visualization a little bit later. So we're going to go over like 4 of the most basic plots you kind of do, right? So scatter plots, box plots, histograms, and densities, or histograms and densities, depending on how you want to do. So really like 2 of these are showing kind of the distribution of the data. Scatter plots just looking at either a univariate or bivariate kind of look at something. So plot is kind of this general overall function that can do a lot of different things. There are specific commands for specific subplots, so like like there's histogram, I believe, in R, box plot, graph box, and stuff like that. We're going to do a lot more of these in ggplot2 in the visualization lecture, but for today, we're going to use plots of these. So we've kind of showed how to summarize the data using group bys and summarize and all that kind of stuff. And now we're going to get into looking at some of the things, or some ways of visualizing the data. So overall, I think there's more or less 2 types of plotting. One being exploratory plotting or exploratory data analysis, and that's what you do like 90% of the time. So it's just kind of trying to get a gist of the data, trying to get a feel for what's going on, trying to identify outliers, that kind of stuff. And that's what I would use on the day-to-day. And then the other 10% I'll say is plotting for publication, right? So making publishable-ready figures, that kind of stuff. The majority of the stuff we'll talk about in this lecture is just exploratory data plots. They're not going to look great, and by design, they're supposed to be done quickly. That's the whole point. All right, so plot takes in 2 arguments, an x and a y. And so here we're going to plot the empty cars miles per gallon versus the displacement. So whatever you put in the first slot, because the first argument is x, it'll be plotted on the x-axis, and whatever you put in the second argument, will be plotted on the y-axis. And we see this overall trend. You see by default, it plots as points. Yes?
John, maybe you mentioned this already, but I noticed you were saying arguments.
Yes.
I'm just wondering if everyone knows what an argument is.
Yeah, so an argument is a thing you pass into a function, right? So when we look at the help file, for example, maybe not for plot, but let's go back here. When I say hist and I say x, x is an argument of that function. It's something that function expects to be passed in. And so let's go back. So maybe read underscore CSV would be a good example to kind of use. Okay. Okay. So when it says arguments in a help file, it's over here. These are the arguments of that function. So when we go back to the function definition, for example, and read underscore CSV, we see file, column names, column types, all that kind of stuff. Okay. So file is an argument of that function. So arguments can be passed in 2 ways to a function. One, by the order in which you put them in, or the second way is you set them by their name. And what I mean by that is if you say read CSV and then put in a file name in there, then it says, okay, this is the first argument. I assume since the first argument of read CSV is a file, that's where you want to pass it in. So for example, if you say read CSV and then just put a file name, it totally works. Right? It says, okay, the first argument's file. I'm going to take this thing and set that to be the file name, and then I'm going to run read underscore CSV. Which much more commonly done, though, is you execute an argument you execute a function with named arguments. And what I mean by that is you say read underscore CSV file equals something. So we specifically say set this argument the file argument to be the file name. So like data Baltimore employees, for example. So this is the one way I was saying. So for example, if you don't name the argument, it still works, right? So it says, oh, this is the file name and go. You can also do this. The reason you usually do the naming, where you say specifically this argument, I want to assign this argument to this thing, is because if you do it that way, it doesn't matter what order you put things in. So let's go back to the help file really quickly. So let's say you're like, all right, I know the file is the first argument, but I want to say skip equals like 5. I want to skip the first 5 rows of a data set, right? If you had to do it by the order, right, you'd have to specify file and then column names and column types, locale, NA, quoted, all these up until skip, and you would just put those in order. That's not really efficient, and that's not really helpful, especially if you don't want to change any of those values other than their defaults. So the way you would do that is read underscore CSV, say file equals data, and skip equals 5, right? So it doesn't matter that that's not the second argument of the function because you named it. You said, okay, I want to assign the argument skip to be equal to 5. It doesn't matter if that's the second, the 5th, or the 100th argument of a function. You can still pass it in that way. Moreover, if you do something like this, it's going to say, hey, you didn't name this anything, so I'm gonna put this argument, this file name, as whatever argument, as the first argument, right? So you don't have to name all the arguments, but if you do something out of order, you have to name it. So usually, for the most part, a lot of functions have 1 or 2 arguments that you usually specify. So for example, a file name, right? Or when we use write CSV, the first argument is the data set, the second argument is the file name, right? So not a big deal. You can just put in data set and a character string for the file name that you want to write out. You can do that without naming either one of them. That's only 2 arguments. But let's say something like read CSV has a bunch of arguments, has a bunch of things you can specify, and you want to specify one of the other ones that's not in order. This is the way you do it. So although, and so when you start using functions more consistently, you usually remember like, oh, the first argument's like, when we do string replacement or something like that later today, the first argument I put into these functions is always the string I want to do some manipulations on. So I never have to name it. But things that you're like, I forget what order that's in, or that's not an argument that's not commonly used, or that's not one of the first like 2 arguments, you usually just have to name it. Okay? So skip is not something in memory, it's not a column, data set, or anything like that. It is an argument of the read CSV function. Does that make sense? So kind of like in Stata, options, right? After the comma and all that kind of stuff that you specify, except it's specified in a very different way. Yeah. All right. So again, we didn't put any arguments on this, and so it knows that the first thing we put in there, it's going to assume to be our x variable. The second thing we put in there, it assumes to be our y variable. So again, this plot is not very pretty, but some say that's by design. Some say that the initial plots of R are ugly, so that you have to make them better, right? No one would try to throw this into necessarily. Well, no one. If people try to throw this straight into a journal, it will be kicked back rather immediately. With respect to this is not a publishable figure, but it does give you a good gist of what's going on with the data. All right. So scatter plots, you can just put in two arguments. The plot function, it's rather simple. We will get into a different system with ggplot2 and how to do this a little bit more in detail. But this gives you a good gist. Okay, it looks like there's a negative relationship between these 2 variables. Let's say we just wanted to look at the overall distribution. Like we took the average of those TB measures from 1990 to 1999. So we said hist on that vector. It does a histogram, and it does some estimation on how to do the breaks. And this is what you get. So it's a very right-tailed skewed distribution, and it looks like a lot of them are really, really low. Some countries have a really, really high incidence of TB with respect to the others. So there is a way. So by default, I said that it plots points. If you say type equals L, it'll plot a line. Right. So here we're plotting the averages from 2000 to 2015. The y-axis we're putting the year averages. So it's the average over each year, over all the countries, and we say this is our x variable, this is our y variable, and this is the type we want to use. So we want to say L, so it's joined by a line rather than just plotting a bunch of points. So densities, I think are really useful, especially when you have a lot of data. Sometimes histograms are always pretty good. You can change the breaks on them to say, like, I want to have 30 breaks or something. You get kind of a smooth histogram, and that's what density is doing. It's doing a kernel density estimate, which is essentially a smooth histogram. And so the density function estimates it. So density, you pass in this vector, right? And this vector is the I think in the example we used, it is the number of cigarettes a day that were smoked by the people, and then density estimates that smooth histogram, and we can say plot on the density, and it'll give us that smooth histogram. And it'll tell us like what the bandwidth was used, the number of points in there, and then it gives us the density estimate. So box plot has a different type of syntax. So here we're plotting each location, the number of cigarettes smoked in this data set from the Youth Tobacco Survey. So the big difference is it doesn't say the first argument's not x, the first argument's not y. It is done. The arguments are passed in what's called a formula syntax. So the way that is, it's y tilde x. So what do I want to plot on the y-axis? The tilde, right? And then what do I want to plot on the x-axis?
What if you just have, like, if you don't have different levels that you want to plot over?
You can just say box plot on one of them, and it'll just do it. So usually if you want to do x, y, but if you want to just do like we did with hist, you can just put one vector in there. Well, we bring this up because later, this is how you actually specify models. That's why it's called a formula syntax. So when we use linear models and generalized linear models, the way you do that is y tilde x1, and then you actually use plus x2, x3 to do model specifications and that kind of stuff. All right, and note sometimes, depending on how the plot is configured, not everything kind of shows up really nicely. So there are arguments to change these around. We're not going to show that here because we'll do that more in the visualization. But the idea is sometimes the way plots are configured, you'll have the ticks. Like this is it's not Tennessee or New York, but it doesn't necessarily show what it is. The other way, so we showed it this way, where we use smoke $, that vector, tilde, smoke $, that vector. The other way you can do that, similar to kind of like the the dplyr way, you can say data, y column, tilde, x column, and then you specify which data set you're using. Okay? So this is how you, again, later you're gonna specify a model. So instead of box plot, it would be like lm, the function lm. If you wanted to do the data value and have a fixed effect for every location, for example, this is the way you do it: y tilde x, and then specify the data set that you're using.
If you specify the data set, can you
Exactly. So by default, boxplot is assuming the first argument is going to be formula. So if you want to put a different first argument, totally fine. You just have to name it. Right? So there's some other plots. So there's a map plot. So sometimes if you have two matrices, for example, you might want to do large matrix plot. Pairs plots does pairwise scatter plots of x and y column by column, or if you do pairs on a single data frame where all the columns are numeric, it'll do a scatter plot matrix like that. Not super helpful, especially if the data is really, really big. I would tend to do this a little bit differently with facets a little bit later, but this gives you a good general gist as like what's going on. I mean, I think there's 10 units here. 10 by 10 gets a little bit too hard to see, but if you do maybe 5 by 5, it gives you a good snapshot to say like, is there something really strange going on here? Do I at least see like trends where like, these shouldn't be negatively correlated, or at least strongly negatively correlated, right? Because you would assume your TV incidence from the year before is correlated with TV incidence later. So this is 99 and 98, for example, and it says like because 99 is here, that's on the x-axis, and 93 is on the y-axis, for example. All right. So I think there's only one question left in the summarization lab. So let's go to that, and then we're going to move on to kind of back to data classes and a little bit lab there. So yeah, I think we're just on part 4, the very last 2 questions. Okay, let's look at the quantiles. Right, so we're going to use bike length. This doesn't have any missing data, so we don't have to use na.rm equals true. But so if we just hit quantile here, it looks like 25th percentile is about 124, and then 200, 341, and then there's a really, 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 really long bike lane. Right, so if we do the histogram of that, by the way, you can hit zoom to pop out a plot so you can actually see it. My RStudio is zoomed in, so it's larger on the screen. So this is a histogram. It's not a very informative histogram for the most part. So, and that's due to how the breaks are kind of calculated. So if we go to the help file for histogram, you can see that there is an argument for breaks, where you can either specify a vector of the breakpoints, a function to compute the breakpoints, a single number, or a character string given for some of these algorithms. So more or less the way I usually do this is one of two ways. I either give the breakpoints or I specify a single number for the number of breaks. And the majority of the time I do something where I say, like, I want 100 breaks. So if you do maybe 100 breaks, this gives you a better kind of overall look at the distribution of the data. So when we looked at it before, it was a huge block at 0. We see there's a few around here. The majority are around maybe 1 to 200, and then there's a few really, really long ones out here. But again, this might not be the easiest way to see the data. So I'm going to do a log2 transform, or actually I'll do a log10 transform, so that, for example, 2 right here means 100, right? 3 means 1,000, and the ones we had way out there with respect to length are all the way up here. So everything is the order of the power of 10. So we kind of see, after we do some log transformation, it looks rather symmetric, looks somewhat unimodal. So I wouldn't say, for example, this data is like log normal or anything like that. But if you're trying to get a gist of how the data lie, this is one good way. This might indicate you might want to do some transformations if you're doing some modeling with your data. Unless, for example, this is your outcome, so you might want to use like a Poisson model or something like that, or a log linear model. But that's the overall gist. So log10 was the function I used for that. There are no, I believe, well, let's see. So there's one length that equals 0. So that's not going to show up in these graphs. So, and many times when you do log transformations, again, you want to maybe add 1 to that, so that values that have 0 will still be contained in there, because if you take the log of 0, you get negative infinity no matter what the base is. So sometimes you want to add 1 and do the histogram. Okay. So let's then, as described as above, after stratifying by type and the number of lanes, do some sort of summarization. Now, one thing I want to note: summarize assumes you are going to give it one thing back. So this fails. This is unfortunate. There are ways around this. They're a little bit, I wouldn't say complicated, but they just seem a little bit confusing to me, at least. I'll show you one way, but more often than not, if I run into situations like this, I'll just put in the probabilities myself and just create and copy and paste it like 3 or 4 times, like so. So I'll do, min is the min, Q25 is quantile, length, probs equals 0.25. Q50, Q75, something like that. That's one way where I would be able to get the quantiles for each different type. So the quantile of the bike length for each of the different bike lane types. That's one way. There's a package we'll talk about later called Broom, which can tidy things up a bit. So the other way you can do this, I believe, is summarize. I'll post an example of this on the website. But more or less, there's this function called do that allows you to use summarize in a way that you can pass back things with multiple outputs, right? So quantile gives 5 numbers back versus 1. But for the most part, if you're trying to describe things based on the quantiles, this would be the way I would do it. So in here, let's say we want to stratify things though using box plots rather than histograms. So box plots have this really nice way of doing an X and a Y and looking at the distributions of things. So we can do box plot. The data set again is bike, and we want to do length on the Y-axis, tilde type on the X-axis. We zoom that in. So there's the command there. So we zoom that in. This is kind of how the data looks. Again, box and whisker plots really are for like a lot of relatively normalish data, unimodal data, highly skewed data. You get some really condensed, box plots looking like this. So again, we might want to do some transformations to the data before doing that if we want to kind of see where medians or that kind of stuff really lie. So again, this is the command. Right, and so just like majority of other statistical packages, these points are determined by, they take the IQR, multiplied by 1.5, and they say, if you're 1.5 times the IQR above the 75th percentile, you're an outlier. Or if you're 1.5 times the IQR below the 25th percentile, you're an outlier, right, based on Tukey's original work. So, not very useful. I don't really see things largely because this thing is really skewed. So what we can do in this, we can say log 10. Zoom here. So that gives, still says like a bunch of outliers and all that kind of stuff, but it gives us a better idea as to where the distribution of bike lane lengths kind of share. So we see there might be a little bit of difference in the medians between these two, and so on. And we can do the same thing with respect to number of lanes. Okay? So this is a preview. We would probably do something like this in the other lecture on visualization. Show up. We might do something. We would probably use some similar code to get something like this. Using ggplot2, where we say, talk about this more, but the idea is we can use this ggplot2 syntax, say, this is the data set, y variables length, x variables type, and I'm going to do a box plot, and although it looks really jammed, And that little box down there. This is kind of what you get. And we can do log 10 transformations and stuff like that. That's what we're going to do later. It doesn't look great, but it looks a little bit better by default than I think some of the base functionality. All right, data summarization lab over. So we're going to take a little bit of a step back, talk about data classes, and this is really where we're going to get a workup on factors. And so that's what we're going to jump to now. Data classes. So, although I agree, some of the things I've described in this class are like esoteric and they seem super technical and that kind of stuff. We used to have the class structured in a way where, like, day one, it was like data classes. And, like, this is a factor, this is a numeric, all that kind of stuff. And we didn't get into like importing data until like the end of like day 2, and everybody, including us, really just wanted to like leave the entire room for the entire day. Because so, although this stuff is more fundamental than some of the things we described, previously, like the dplyr package, the readr package, and stuff like that, we find that kind of getting data into R, getting people at least comfortable saying like, oh, I can import a data set into R, makes them a lot more comfortable, makes them a lot more happy. So that's why we're kind of coming back to data classes and a little bit more of a formal workup. So again, we've talked about a lot of these. A character, right? So I'm going to call these data types. Although you use the class argument to get to them, for most of these are more or less data types. So, okay. Data types are, what does a vector hold? Does it hold a character, a number, a factor, a logical, maybe a date? Data classes are the holders, right? So a data frame, a table, that kind of stuff. So although the class function, when we use it, return character, a numeric, and it can return factor, or logical, I'll be trying to disambiguate. These are types. So again, this doesn't really have an analog to data for the most part, but these are the things where the majority of your data is going to lie, right? You either got numbers, words, or categorical variables, trues or falses, ones or zeros, or you have some sort of date. Right? There are some sometimes there are other things you may contain in your data. Latin long, I would still call them numerics, for example, but there are some other things, but those are like the 5% compared to like this is 95% of the data you have. So okay, characters, strings are individual characters. They are quoted when you print them. Numerics, any real numbers. Integers. Integers are just a special case of numerics. They just happen to be whole numbers. That's all. So when we do, for example, when we were trying to do subsetting before, and we did a -1, a 0, and a 1, it said something like, subsets can only be, with zeros, can only be mixed with negative numbers, or negative integers, or something like that. So when you do subsetting, it treats them as just whole numbers, right? You can try to subset, you can do something like subset the vector x at like position 2.5. What it does is it'll actually round that number down to 2, and it'll give you the second element. Stuff like that. Don't do that. Try not. Pass in whole numbers. Either using which, or use logical subsets, or using like a sequence of numbers, which we'll show a little bit. Factors. Categorical or qualitative variables. We're going to treat them up a lot more in this lecture. This is where you encode. This is the I dot of R. Factors are the way you encode categorical variables, and you can specify the levels. You can use them for plotting, right? So, and they will keep the structure that you give them in the sense like you say, I want the reference category to be this, the second category to be this, the third category to be this. When you do tables, first category will be whatever you specified, second, and so forth. When you do plots, the first one coming up is going to be whatever level you chose as the baseline, second, third. Whenever you do models, it's going to be the first level is the baseline level, and so on and so forth. Logicals, trues or falses. Don't have quotes around it. If you do mathematical operations on these, like mean or sum, treats these as ones, these are zeros. Dates, we're going to talk about a little bit more detail, but those usually are the biggest headaches for any piece of data that you have, because it is astounding the number of ways people like to encode dates. But there's some really nice packages that help and make it a lot easier to work with. Okay, so remember, again, the class function gives us an idea of what the data type is. So again, we just had this vector of Andrew Jaffe. It's a character, class, it's numeric. So integer, again, it's a special subset of numerics that can only contain whole numbers. So before, we used that colon operator, 1:5, for example, which gave you a sequence of numbers, 1, 2, 3, 4, 5. That is an integer, right? More or less, they aren't special. They don't do anything relatively unique compared to just working with real numbers. Just if you say like class on something and it says integer, that's what it means. So although the colon operator is great, sometimes you want to do sequences of numbers that don't jump by 1, right? So the seq function, seq, is a function that you want to do. It takes in usually 3 arguments, from, to, and by default, there's an argument by. The default in there is 1. So you just want to say, if you say from 1, 2 is 5, it's going to say jump 1, 2, 3, 4, 5. If I said by equals 0.1, it will give me a sequence of numbers by 0.1. It'll give me a sequence from 1 to 5 by 0.1. Now, it will do that as best it can. So, if you go from 1 to 5.25 by 0.1, you can't exactly do that. It doesn't divide evenly. Right? So there's 1, 1.1, keep going, keep going, keep going, keep going, keep going, keep going. It never goes past the endpoint, but it'll give you, 5.2. It won't jump up to 5.3. Okay? So seq, nice little handy function to have around. And if you set the class of anything out of seq, where the jump is a whole number. All right. Again, the colon operator we already talked about does the jumps. It's a shorthand. So again, logical. Only has 2 possible elements, true and false. We've used these already for subsetting, but you can also make logical vectors just like you can with characters and numerics using the C function to collect things together. The way you do it, true, false, all caps, no quotes. Yes?
So if you're importing, like, say, a Stata data set, all the variable is coded 0, 1. All variables that are coded 0, 1 get imported as logical, or how does it get?
I don't believe, to my knowledge, again, I tend to not use Stata data sets that much with respect to R, but I believe it's coded as just 0, 1 as a numeric.
Okay.
So you can do that. Like you can just say mutate column equals column greater than 0. And then that will be re-encoded as logicals, trues, and falses.
Okay.
For the most part, having the data stored as a 0, 1 versus a true, false doesn't have that many differences, except when you're trying to do filtering, for example. Right? If you have a logical true or false, a column that's like trues or falses, and you say filter and you just put that column name in there, then it knows find the ones where it's true. Right? So really, so for all intents and purposes, a lot of times if you coded 0, 1 versus true or false, then it's not going to make the largest difference, right? Because if you take the sums of this, it's going to give you the same thing as, So if you say the class of it, it's logical. So there are functions that allow you to test whether something is a specific data type. So is the general function. Is.numeric says, is this a numeric vector? It'll come up true or false. It'll come up true if it's numeric, false otherwise. So for example, you're like, all right, I got this data set and I imported it yesterday and I imported it today, and I want something in code to say like, is it still, somebody updated all this data, is this column still a number? Did it come in as a numeric? Did it come in like as a number? Did somebody put some weird data in there and now is it a character? So you can use is.numeric on that vector to do some testing, for example. Right? This is not a numeric vector, right? So it comes up false. It is a character vector, so it comes up true. There are also as functions. So this is d-string, toString, that kind of stuff. So we're talking about coercion again, but we're doing it explicitly. Instead of jamming numbers and characters together and say, oh, let's make it a character, you can do that explicitly. So again, true, false, true, false. This is a character vector. It's got quotes around it. It does not understand, R does not understand that you want to use that as a logical. Okay? So you say, I got these as trues as falses because somebody put some weird thing in there. I just want to convert it to a logical. You say as dot logical, and they'll say true, false, true, false. You see this is without quotes. It changed that vector. Now it's a number, right? So if you try to do the sum on this, nothing's going to work. It's going to say the words. I don't know what you're doing. After you do as dot logical, you can do the sum on that, and it'll count the number of truths. Okay? Already said this, so there's 2 truths there. So if you do mean on a logical, that's a percentage, right? On things like that. So again, is and as are the general functions. So is tests something, as changes it to that. So it doesn't matter. Like in Stata, I believe, you say like replace or like gen new variable equals real new variable, right? Where you want to make something into a number, and it said if that column that you're trying to make real is already a number, it's going to fail. Right? It says, hey, you got to pass in characters to this. This doesn't matter. If you have a character vector and say as that character, it's going to say, okay, this is already a character. I'm not going to do it. So this coercion, you can put in kind of anything in here and try to coerce it to the other format. Like I said before, if you try as.numeric on, for example, this, it's going to say, I have no idea how to make these numbers, and it's going to give you back this. But it'll give you a warning. All right. Again, you say as.character, 147, but gonna put quotes around it. Says, okay, you want to make this a character? That's fine. No big deal. Again, if you say as.numeric on something like that, it's going to say, hey, I don't know how to make the word Andrew into a number. I'm going to give you a name. Okay. That stuff, for the most part, other than the is and as functions, we've already discussed pretty, here and there. The one big function, the one big type that we haven't discussed, which is one of the most important, is factors. So, factor is the function to create a vector. So you pass in a vector. So it's already a column you already have, or it's a string of characters or something like that, or it's a string of numbers, and you say x equals factor, boy, girl, boy, girl. So like the other formats, it prints differently to give you an idea that if you're just printing stuff out, you kind of have an idea of what class this thing is without having to do all this checking. So numbers don't have quotes, characters have quotes, logicals are just trues and falses. Factors have no quotes, but they also have this second thing that say, these are the levels. If you see something with levels, almost 100% of the time that means it's a factor. So, this is not a character vector of boy, girl. So, one thing to know, what's the first factor? What's the first level? Boy. It's chosen alphanumerically, right? It's not because boy was the first element here. Girl could have been the first element. Doesn't care. It does a unique. It says, what are the unique levels of this by default? And it says, sort them alphanumerically. Whatever comes first is your first category, right? So we said male and then girl, for example, or male then female. Female would come first because F becomes before G. Okay? Next slide will show you how to specify the exact levels that you want. Yes?
Sorry, another question about importing. So usually in Stata or CSV or whatever format, our data sets come in, the categorical variables are coded as numeric, right? With each category getting a
Correct.
different value. So if it's, say, a labeled numeric variable,
Correct.
when it gets imported, does it get imported as numeric or as a vector?
By default, it gets imported as numeric. But, okay, let's do this. So, have an example, DHS. All right. So I'm going to pull this up in Stata so we can see it. Pull up this DTA. Give me a minute.